So as I promised, we're going to start solving equations with these things, with these exponential functions. So your first goal that you want to do, or you want to try to have happen, is you want the bases to match, if possible. Sometimes it's not possible, and we'll get into that in a couple other sections. But for now, we're going to try to get them to match. So with a base of 5 and a base of 25, hopefully, if it works out, there's going to be a common base. And in this case, there is. It's a common base of 5. Because 25 is just 5 squared. So once you get the bases to match, the theory is, well, if it's equal and the bases are the same, then the exponents would have to equal each other. So the bases can drop out. You can ignore them and just take the exponents, set them equal to each other, and solve for x. So for this one, x is going to equal -1. Okay, so not too hard. Where it gets a little tricky sometimes is when you have some radicals involved. So clearly the common base is 6. So this 6 on the outside, that's just 6 to the first. The square root, if you remember your radicals stuff, the square root turns into a 1/2 power. And the bases can't drop out yet. You got to get it so it's like this, where it's like a single base on either side. And here we have 2 6s. So we need to combine them. So the concept is the same as if you had like x squared times x to the 4th. What would that equal? X to the 6. So how did we get the 6? Well, you added the exponents up. Well, you can do the same thing if they're numbers as opposed to variables. So 1 plus 1/2 is 3/2. So now that you have it as a single base, now the bases can drop out, and then you can solve x minus 4 is equal to 3/2. So as long as you can deal with fractions in addition and subtraction, you should be able to get an answer. And it comes out as 11/2. So we'll see how many people actually watch the video and know how to deal with going from here to here. Because I bet I'm going to get a lot of questions on that. And they'll be like, did you watch the video? And they'll say, no. Say, well, guess what you get to do. Okay, so let's look at part C. So this one's kind of fun because you can't change 27 to a power of 9, and you can't really change a 9 into a power of 27. But there is a common base that they can both turn into, and that would be 3. So the 9 would be 3 squared. And then the 27 would be 3 to the 3rd. Well, you don't want to drop them out just yet. You don't want any parentheses involved, or you don't want like powers to powers. They only drop out when it looks like, you know, like this or like this. Like things have been like combined together and simplified as much as possible. So in this situation, instead of adding the exponents up like we did here, this situation calls for multiplication. So the 2 gets multiplied into the negative x and the 15. And the 3 gets multiplied to that x, so it would be 3 to the 3x. So we've got it down to the common base. There are no more parentheses involved, so we can drop the 3's out and solve that remaining equation. -2x plus 30 is equal to 3x. So x is going to equal 6. All right, so here's the special thing that I talked about in the last video. There's a special exponential function, and that's the natural exponential function. and that is f of x is equal to e to the x. So the e, that's an irrational number. It's like pi. It's a never-ending decimal with no pattern. So that is considered the natural exponential function. So we can graph them because you can graph any exponential function, and it follows the same rules as all of the other ones. So just because the base is an e, like don't panic, it's not going to change it. It's still just like if the base was a 2 or 5 or 17. So the horizontal asymptote is at -4. It's got a positive in front of the base, positive in front of the x, so it's going like this. We just have to have it hit the y-axis at the right place. So stick in 0 for x. And then e to the 0 is still 1. So we get a total of -3. So your y-intercept is happening right down there. And I didn't say this before, but when you graph these exponential functions, we're not interested in the x-intercept yet because we haven't talked about, or we don't, even if we talked about it, we don't have the right tools to figure out what that intercept actually is. So for the exponential functions, we're just going to be talking about the y. Okay, last example. Solve the equation e to the 4x times e to the x squared is equal to e to the 12th. Wow, that's got a lot of stuff in there. So we're going to kind of try to change it into something like this. So just work it down to a single e on either side. So first, multiply the 4 and the x together. And we need to combine the e's together, just like we did with the 6's from up here. So we are going to add the exponents up. And I'm going to put the 4x second. So x squared plus 4x is equal to e to the 12th. Well, now you have that common base. So just like the other examples up here, the e's can drop out. And you're left with x squared plus 4x equals 12. Excuse me, and we have to solve this equation. Well, what kind of equation is it? It's quadratic. So set it equal to 0, and we're going to solve it for x. So I'm going to factor that. X plus 6, x minus 2. So x is going to equal -6 and positive 2. So, you know, you can take these crazy looking equations and still be able to solve for it just by using a couple little techniques. And you can, you know, you can get more than one answer from these, or you can just get one. Just depends on what type of equation you're solving once the exponential stuff's dropped out. Okay, so that's going to do it for section 5.3. So give the homework a shot and let me know what your questions are.